Welcome to the deep dive. Today, we're not just asking what generative AI can create, we're asking how it's actually engineered.
Right.
Our mission is to take you inside the server racks, inside the source code. We are exploring the granular technical blueprints, the specific optimizers and kernel hacks used to build state-of-the-art systems.
And that's really the core tension in the industry right now. Because on one hand, you have this massive architectural convergence. I mean, fields that started out completely distinct, NLP, computer vision, audio synthesis, they've all sort of coalesced. The underlying paradigm is, well, it's usually the transformer, or maybe diffusion.
So in theory, the way you predict the next word is basically the same as how you predict the next sound wave.
Fundamentally, yes.
Yeah.
But that's the theory.
And that's where it gets interesting, right? Because in practice, if you want to build a system that actually wins, you can't just rely on that high-level abstraction.
Exactly. That theoretical convergence hides a world of highly specialized, really low-level engineering. Building a reliable agent is a completely different game than building a photorealistic video generator.
So today we're dissecting the machine. We're talking JSON schemas, GPU kernels, all the nuts and bolts. This is the blueprint for sovereign AI. Okay, let's start with the brain of the whole system, the large language model. The decoder-only Transformer Think GPT, or Llama, that's the foundational substrate.
It is.
But if you're building one from scratch, you can't just, download the architecture. You have to pick the components for the engine. So where do we start?
You have to start with how the model understands order and length. That means positional embeddings. And we've seen this really critical shift away from the old absolute encodings to rotary positional embeddings.
Rope.
Ropey. Okay, that sounds pretty technical. How does a math hack like that translate into a real-world benefit for, someone listening? Well, it solves the context length problem. Ropey lets a model work effectively on sequences that are much, much longer than anything it was trained on.
And why does that matter to you?
It's essential for RAGI, retrieval augmented generation, where you're pulling in massive documents, maybe 100 pages, on the fly. Without Ropey, the model just gets confused. It completely forgets what it read at the beginning of that new, huge context window.
So Ropey gives us the theoretical ability to handle that massive context, but the attention mechanism itself, that's famous for being quadratically expensive.
Right.
How do we stop the model from just grinding to a halt with 100,000 tokens?
With an engineering triumph called Flash Attention 2. Now, the raw math of attention is still quadratic, right? Double the context and you quadruple the computation.
Right.
But Flash Attention 2 attacks the real bottleneck, which isn't the computation, it's the memory transfer.
I hear a lot about high bandwidth memory, HBM, in this context. Can you simplify what flash attention is actually doing there?
Sure. Think of the GPU's memory as a library. You have this huge main reading room, that's HBM, and then these tiny superfast desks right next to the processor, that's SRAM.
Okay.
Standard attention makes thousands of trips back and forth from the desk to the reading room. Flash Attention 2 rewrites the whole process. It optimizes the memory access pattern so you keep the data on those tiny fast desks for way longer.
So you're just cutting out all those slow trips to the main room.
You are. By reducing those HBM reads and writes, you slash the memory latency. And that's the plumbing hack, really, that makes 100K plus token context windows feasible today.
That's just pure engineering.
Yeah.
So moving to scale, we hear about models with trillions of parameters, which just sounds impossible for anyone to actually run. How are people building models that large and keeping them usable?
That's the beauty of mixture of experts, or MOE. Think of it like this. You hire a huge consulting firm with 1,000 experts. If you ask a question about marine biology...
You don't need the tax lawyer to weigh in.
Exactly. You just need the marine biologist. MOE uses a tiny router network that directs each incoming token to only a couple of relevant expert layers, maybe 2 out of 8. This decouples the total number of parameters from the active parameters you need for any given task.
But that routing must add latency, right? It sounds like a trade-off. Speed for size.
That is the trade-off, yes. MOE models can have higher latency because of those routing decisions, but for just raw learning capacity at a manageable inference cost, it's the state-of-the-art. You get the knowledge of a massive model without needing a supercomputer to run it.
Okay, let's pivot to the data. We always hear that, 80% of the work in building an LLM is the data layer. If the architecture is all sorted, why is the data part so hard?
Because the quality of your pre-training data sets the absolute reasoning ceiling for the entire model. First, you need breadth. Common crawl, the whole internet.
Right.
Then you need depth. Curated, high-quality sources. GitHub repos for code, PubMed for medical science. But the really crucial, painful part is deduplication.
Why is getting rid of duplicates so critical?
Because if a model sees the same paragraph 50 times, it just memorizes it. It stops generalizing. We call this a grokking instability, and it's basically a failure of engineering rigor. You have to use tools like min-hash LSH to find all those near duplicates, or your model will just be brittle.
And what about tokenization? Can't we just use a standard one?
Not for specialized domains. Take a medical model. A standard tokenizer might see the word laparoscopy and break it into, say, 4 random tokens.
It loses the meaning.
It loses the semantic integrity. A custom medical tokenizer, though, knows that laparoscopy is a single meaningful unit. That makes the model far more efficient and, well, far more intelligent in that specific domain.
So we've built the brain, the cognitive substrate. Now we need to talk efficiency. After the base model is trained, we have to fine-tune it. And right now, what's the one piece of tech making that process dramatically faster?
Oh, without a doubt, the hero of the moment is Unsloth. It is an incredible piece of low-level engineering.
What are they doing?
They're manually rewriting the backpropagation kernels, the core math routines, using a language called Triton.
Wait, so they're not just using standard PyTorch functions, they're going deeper and writing custom GPU code.
That is exactly what they're doing. They're bypassing all the generalized, inefficient parts of the standard libraries. And the result is, well, it's striking. You get 2 to 5 times faster training and up to 80% less memory usage.
That's a huge deal. It means you can fine-tune something massive like a Llama 370B model on a single high-end consumer GPU.
It's a fundamental shift in accessibility, a total democratization feat. Now, for big enterprise jobs, you might still use Axolotl for its robust configuration, or TorchTune if you need to hack the PyTorch internals. But Unsloth is the one changing the game for everyone else.
And that accessibility is also driven by PEFT, parameter-efficient fine-tuning.
Exactly. And the industry standard there is QLoRa. It's brilliant. You take the huge frozen model backbone and you quantize it down to 4-bit precision. Then you attach these tiny trainable adapters called LoRa.
So you're only actually training these adapters, which were, what, a tiny fraction of the original model size.
A tiny fraction, maybe 0.01%. You reduce the number of trainable parameters by a factor of 10,000. That is the fundamental reason you can now fine-tune a huge model on a GPU with just 12 or 16 gigs of VRAM.
Okay, so once the model can follow instructions, we have to teach it how to behave. Alignment. For a while, all we heard about was RLHF, but that seems to have faded. What was the problem with that old pipeline?
The problem was just insane complexity and instability. Traditional RLHF required you to train 2 full-scale models. First, you needed a separate reward model just to predict human preferences. Then you had to use this algorithm, PPO, to optimize your LLM against that signal. It was a nightmare to tune.
So what's the replacement? How are we doing alignment now?
The new default is direct preference optimization, or DPO. It's a much more elegant mathematical simplification. It completely sidesteps the need to train that separate reward model.
So you're just taking a whole model out of the pipeline.
You are. It optimizes the LLM's policy directly against the human preference data. The whole process is more stable, it's faster, it's computationally cheaper. For the open source world, DPO is the new standard.
We've built the brain, we've made it efficient, now we need to teach it to see. Multimodal LLMs like LLaVE, they don't just classify an image, they reason about it. So how do you merge the discrete world of language tokens with the continuous world of pixels?
The key innovation there is the projector. It's the translator. The vision encoder, like a CLIP model, turns an image into a bunch of feature vectors. But those vectors live in a totally different mathematical space than the LLM's language embeddings.
So the projector bridges that gap. What is it exactly? Some huge, complex network?
Surprisingly, no. The best ones are often quite simple. A 2-layer MLP, a multi-layer perceptron, is typical. So linear layer, a GLU activation, another linear layer. That's it. Its job is to perform a nonlinear translation mapping raw visual stuff like edges and textures into semantic concepts like dog or chair that the LLM already understands.
And the training for this has to be very specific, right? I hear it's a 2-stage process. Why split it up?
You have to prevent what we call catastrophic forgetting. The LLM already knows language. If you just dump a ton of visual data on it and try to update everything at once, it immediately forgets how to speak.
So you ease it in.
Exactly. Stage 1 is feature alignment. You freeze the vision encoder in the LLM. They don't learn anything. You only train the projector using billions of simple image caption pairs. This is fast, it's cheap, and it just teaches the projector. These pixels mean dog.
And then stage 2 is where the real reasoning starts.
Right. Stage 2 is visual instruction tuning. Now, you unfreeze the projector, and you let the LLM's weights update a little bit, and the data is completely different. It's complex visual dialogue, often synthetically generated by prompting GPT-4 to have conversations about an image.
And the data format here is critical.
Absolutely critical. The JSON schema has to use a special placeholder, like an image token. That token is the trigger for the data loader to stop processing text and insert the projected visual embeddings right into the sequence.
Okay, let's shift from static generation to dynamic agency. Reinforcement learning. It's a different beast entirely. It's about maximizing a reward, not minimizing an error. If you're building a robot or a treating bot, what is the single biggest design challenge?
Well, it's the philosophical core of the problem. Reward shaping. The agent learns from a single number, right? The reward. If that number is poorly designed, the agent will find some bizarre, degenerate way to maximize it without actually doing what you want.
Can you give us an example? How intricate does that reward shaping need to get?
Let's take the classic bipedal walker simulation. The goal is to teach a robot to walk. If you simply reward it for moving forward,
It'll just fall over and slide on its belly or something.
yeah, precisely. It learns to hop erratically or slide. It maximizes forward velocity, but it looks nothing like walking. So your reward function has to be this composite signal. You reward forward velocity, but you penalize energy use. You add small penalties for head tilt. And critically, you add a massive failure penalty, a -100, the second its body touches the ground.
Well,
Plus, a big bonus for success. It's this intricate shaping that guides it away from the shortcuts.
That's a huge engineering challenge, designing the rules of behavior. So for people actually doing this, what are the standard tools?
For continuous control, like robotics, the gold standard algorithm is PPO, Proximal Policy Optimization. It's robust, it's stable, because it constrains how much the policy can change in each step, which prevents those classic RL training collapses.
And how do engineers implement that effectively?
Usually with a library like Stable Baselines 3. And the critical practice there is parallel vectorization. You run hundreds of environments at the same time. This breaks the correlations in the training data and makes the whole learning process way more stable and efficient.
Okay, let's move into the sensory world, audio and video. Let's start with voice cloning. Models like RVC achieve this uncanny fidelity. How do they separate what is said from who is saying it?
They use what's called the soft VC paradigm, separating content from timbre. First, an encoder like Huber processes the audio and strips out the speaker's identity, leaving just the semantic content. But the magic, the reason it sounds so real, is the R in RVC, the retrieval.
Right, the retrieval component.
Exactly. RVC uses a face index, basically a database of the target speaker's unique features. When it generates a new audio, it searches that database to find the closest matching patterns. This lets it hallucinate the specific acoustic details, the breathiness, the accent, that a pure neural network would miss.
So it's not just generating a voice, it's actively looking up parts of the real voice to splice in conceptually. What's the engineering challenge in training one of these?
It's all about balance. The sweet spot is about 100 to 200 epochs. Undertrain it, and the voice sounds robotic and metallic. Overtrain it, past 200 epochs, and you get this high-frequency, screeching artifact. It's like baking. Too little, and it's dough. Too much, and it's burnt.
And what about video, which adds that whole dimension of time? How do engineers inject motion into models that were originally just for static images?
There are two main approaches right now. The first is Anime Diff, which is a retrofit. It takes a pre-trained, frozen stable diffusion model, and it injects new motion modules into it.
So the original model still handles what the image looks like, and these new modules just handle the movement.
That's it. They're temporal attention layers. And this allows for these really lightweight motion LoRa's that can be trained to encode specific camera moves like pan left. The standard way to deploy this is with a comfy UI workflow.
And what's the next generation, the stuff built from the ground up for video?
That would be the open Sora approach. It uses a diffusion transformer, a DIT, with native spatio-temporal attention. So space and time are considered together from the start. But this approach has a huge bottleneck. The 3D VAE, the video VA. This is the component that compresses the raw video across height, width, and time. If your VAE is not perfect, if it generates even slightly blurry latent representations, then the final video will never be sharp. It doesn't matter how good the rest of your model is. Perfect compression is the absolute prerequisite.
Okay, we have covered so much ground. Let's finish with the infrastructure layer. What are the key hacks that make deploying these huge models even possible right now?
Well, we mentioned quantization using bits and bytes for 4-bit is essential. But for serving models to many users at once, the real game changer is an inference server called VLLM.
Why is serving such a bottleneck?
It's memory fragmentation from the key-value cache. Every token the model generates needs this KV pair stored in memory, and sequence lengths are all different. It creates a complete mess on the GPU. VLLM solves this with something called page detention.
Page detention. That sounds like something from an operating system's textbook.
It is. It's inspired directly by virtual memory. Just like an OS manages memory with fixed-size pages, page detention manages the KV cache with fixed-size blocks. It allows for non-contiguous memory, which maximizes GPU use and eliminates waste.
And the result.
It dramatically improves throughput. We're talking up to a 24 times increase over naive serving. It's a true plumbing innovation.
Okay, so for our final synthesis, you started by saying everything is converging, but then you describe all the specialized engineering. So what is the ultimate interconnected system that a sophisticated builder is creating today?
The convergence is in the ecosystem. The modern builder doesn't create silos. They train a multimodal model, an MLLM, and they use its understanding to act as a high-fidelity reward model for an RL agent.
Ah, okay.
And that agent then interacts with an environment, generates new high-quality synthetic data, which then feeds back to train the next generation of vision transformers or video models. It's a deeply interconnected loop.
So success in generative AI is no longer just about who has the most GPUs.
No, not at all. It's defined by the sophistication of the engineering pipeline. The purity of your data, the efficiency of your kernels like Unsloth, the creativity in your projector architecture, the rigor of your reward shaping. That technical intelligence is the real moat now.
The sources laid out the blueprints for how state-of-the-art AI is built. The challenge for you to consider now is the execution. Given all these components, the row-P embeddings, the DPO alignment, the 3D VAEs, the page attention serving, how do you orchestrate them to build a single system that exhibits not just mimicry, but genuine agency, reasoning, and creativity? That is your next deep dive.